Well, good morning, everybody. The time has come for us to talk about three-eyed fish and hulks. And no, it's not going to be that cool. It's going to be cooler. Pun intended. Because reactors require cooling. Guys are hopeless. We need to get started. So we've talked about atoms. Now we're going into the nucleus of the atom. That's what nuclear physics is all about. And so just to give you some sort of terminology and I've been using a certain sort of symbology for what's going on in this section about nuclear physics. Let's just get all of this out of the way and then we'll dig into the science. So in nuclear physics, we have a specific way of writing down the nuclei of these atoms. So we'll start with its chemical symbol. Like if we wanted to talk about the nucleus of carbon, okay, we would write its chemical symbol, and as a superscript on the front, we would put its atomic number down below, and its atomic mass, rounded atomic mass, up above. And this symbology is a handy, compact way to know several things about this carbon nucleus. Okay? First of all, we know it's carbon because it has 6 protons in its nucleus, and it's the atomic number, the number of protons in the nucleus, that determines what the element is. If we were to add a proton to this nucleus, it would no longer be carbon, it would be what? Nitrogen. So it's the number of protons, in other words, the atomic number, that sets what the element is. That 12 is the rounded atomic mass. So carbon on the periodic table up here is 12.0108. We just round it to the closest integer. You're using all the regular rounding rules. And that number is a combination of two things. That atomic mass is the total number of protons and neutrons in this nucleus. So if that's the total, and I know there's 6 protons, how do I find out how many neutrons there are? You subtract to get the number of neutrons. So when we're talking about this nucleus, I would say it's a carbon-12 nucleus. And I want to distinguish that from, say, a carbon-14 nucleus. What does a carbon-14 nucleus look like? It's got a mass of 14. It still has 6 protons. Why? Still carbon. Okay? But now what's different here? It's the number of neutrons. This one has 8. So we have a word to describe the relationship between these two nuclei. They are isotopes of each other. The word isotope means same element, different number of neutrons. Okay? Now, we do have to have a little bit of a discussion about atomic mass units and atomic mass and all that sort of stuff. So first of all, the numbers on the periodic table are all given in atomic mass units. Okay? So carbon's atomic mass on here is 12.0108, like I said before. But what is the mass in atomic mass units of carbon-12? 12. It's 12 atomic mass units exactly. By definition, the atomic mass unit is defined against carbon-12. Carbon-12, that nucleus has exactly 12 atomic mass units. So why does the periodic table have 12.0108 on it?
To account for the percentage of carbon-14 that still exists.
Because there are other isotopes. Okay? And you can, so the number that's on the periodic table is what we call a weighted average. The weighted part means it's not like a strict average. It's you take the relative abundance. So carbon-14 is less than 1% of naturally occurring carbon. Most carbon that you see is carbon-12. There's a very tiny, tiny amount that's carbon-14. And there are other isotopes that do exist for carbon. But carbon-12 is the main one, the natural one. And the carbon-14 is a very long-lived but radioactive isotope of carbon. You've probably heard of it. Carbon dating. Carbon-14 is used in carbon dating, determining the age of how old something is since it died. We'll talk all about that stuff later. But the key thing for you to know right now is that the atomic mass on the periodic table is this average. And you can tell that carbon-12 is like the main isotope or the naturally occurring isotope because the atomic mass is really close to 12. So if you look at nitrogen, nitrogen's atomic mass is 14.0067. So what does that tell you about like the main isotope of nitrogen? Which one would it be? Nitrogen 14. And there must be a little bit of a nitrogen 15 somewhere, or 16, or some other heavier isotope, because it's got that little tiny bit of heavier. But oxygen is listed as 15.9994. So what's the predominant isotope of oxygen? 16. But that atomic mass gives you a hint. There's a lighter isotope. We'd have to go to the tables to look it up. Could be oxygen 14 or 15. Like there's another lighter or maybe more lighter isotope. Some maybe heavier. But you can kind of get a feeling, right, for what the isotopes of an element are doing just by looking at the weighted average of the atomic mass. So there is a conversion. It's not terribly useful between kilograms and atomic mass units. One atomic mass unit, which by the way has a symbol of lowercase u, is 1.660539 times 10, it's supposed to be 10, to the negative 27 kilograms. Okay, several things going on here. Number one, that is a very small number. Okay. Number two, you see how many significant digits there are? Why?
Precision.
Because they are significant. When you're doing nuclear physics, you want to make sure to use every number they give you in your problem, because you can run into round-off errors really fast. So in other areas in physics, we would probably just use 1.66 times 10 to the minus 27 and call it good, right? In nuclear physics, you better use all of that number in your conversion, because it's often only in the very last couple significant digits where things are changing. Now, here's where it gets really kind of, weird. You can also write down an atomic mass unit in a different unit other than kilograms. An atomic mass unit is also equal to 931.494 mega electron volts per C squared. Huh? Where'd that come from? What's a mega electron volt? What kind of unit is that?
Unit energy.
That's energy. And what's C squared? Speed of light squared. And what's an energy? What's E divided by C squared?
M.
It's M. Remember E equals MC squared? It's back, baby. Right? We're back with Einstein and relativity and rest mass. Nuclear physics is all about the transition of mass to energy and figuring out what the energy is of a nucleus and how we can take advantage of that energy. So the atomic nucleus is really small. I know you know that. How small? Well, it kind of goes by the atomic number. Sorry, the mass number. This is the mass number. So you have symbol, you have mass number, and then you have atomic number. I do not know why they don't use A for atomic number as a symbol. It's not my fault. But Z is the symbol for number of protons. A is the, anyway. Okay? But you can put that mass number in there, take its cube root, and multiply by a constant, and get a little bit of an idea of how big a nucleus is going to be. But the constant that kind of goes down in the front of there is measured down in the femtometers, 10 to the minus 15. Okay? So obviously, as your mass number gets bigger, you put more protons and neutrons in there, then the radius of the nucleus gets bigger.
No, I'm just curious. If AMUs have like a lot more significant things, why does our atom only have 2?
No, when you're doing this, you just put 14 or 12 or something in there.
Oh, okay.
Okay. All right. So that's a little bit of the language that is used to talk about the nucleus, keeping track of its protons and neutrons. Yeah, that's in meter. Sorry. Okay. But we need to be able to convert back and forth sometimes, and I'll do some examples where we actually use that kind of screwy mass unit over there in a second. Let's get into kind of what a nucleus looks like. Oh, and by the way, this is a table. You can see tables like this on the internet, in your book, whatever. Okay, I will always give you information like this, right, on an exam question, anything like that. But you can see here, right, that protons and neutrons, electrons, they all have different masses, and that mass can be expressed in kilograms, atomic mass units, or mega electron volts per c squared.
Can you explain what R was again?
R was the radius of the nucleus.
Okay.
Yeah, and it's like a effective radius or it's a ball. It's a back of the envelope calculation for how big a nucleus is. It's not precise, but it gets you within the ballpark, and that's good enough for us. So again, you can write all these out, but you notice how the atomic mass of carbon 12 is exactly 12. Again, by definition, by standard. This is kind of what a nucleus looks like. It's a bunch of ping pong balls glued together, more or less. Like unlike an electron, which is this wave particle duality thing, zipping or and falling, whatever. Okay? A nucleus actually can be more or less thought of as a bunch of spheres stacked together. It's a little bit more complicated than that, of course. I'm not going to go into a whole lot of detail. There's a version of quantum mechanics that applies only to nucleons, to protons and neutrons, and they have different energy levels, and there's tunneling that can happen in the nucleus. It can get really involved. But those models, while being ultra precise, this is kind of good enough. And protons and neutrons generally, they do have wavelength, but generally they're not going fast. I mean, they're in a nucleus. They're not really going anywhere. And so they're not expressing that behavior. Most of that's a lie. But more importantly, there's another problem. And the problem is that protons don't like to be with protons. And if you're talking about distances measured in tenths of a femtometer, right? These two positively charged things are really, really close to each other. And you don't have to be a Physics 4B graduate to know that when a positive charge and a positive charge get close to each other, what happens?
They push.
They push apart, right? And they push hard. And it goes as the inverse square as the distance between them, which means as the distance between them gets smaller and smaller, the force gets bigger and bigger and bigger. So what should a nucleus do? It should fly apart. Because a neutron's not going to hold on to anything, according to Coulomb's law, right? And you've just got a bunch of positively charged things that are too close to each other that don't want to be there. But obviously nuclei don't do this. So the question becomes why? How do you keep positively charged things from not flying away from each other? You glue them together. Just get some really good super glue. You can pull this off. In nature, we've identified the third fundamental force that you ever learned in your physics career at this level. Actually, at any level. You've learned about gravity in Physics 4A. If you haven't had Physics 4B yet, that's where you would learn about electromagnetism, okay? But you'll learn about next semester if you haven't had it yet. That's the second fundamental force, okay? The third fundamental force, here we are 2 weeks before the end of Physics 4C, we're finally getting to it, is the force that keeps the nucleus together. We need a catchy name for it, don't we? The glue force. The God force. That's too on the nose. What should we call it? The force. That's the one that connects all living beings. It has nothing to do with midichlorians. I don't care who you are. George Lucas. What do we call the force that keeps the nucleus together?
Strong nuclear force.
All that human creativity and art and imagination, we come up with the name strong force. Why is it called the strong force? It's stronger than the electromagnetic repulsion between protons.
Isn't there a weak one too?
There is a weak one, we're getting there, okay? So, protons are repelled by the electromagnetic force, but the strong nuclear force acts not just between protons and protons, but also between protons and neutrons. So the strong force doesn't care about what the charge is. It acts between nucleons, nucleons being a catch-all word for anything that's in the nucleus, so a neutron or a proton. The strong force is extremely short range. So if you get a nucleus that's too big, there is the possibility that a proton on one side of this nucleus and a proton on the other side of this nucleus will feel the electromagnetic repulsion because that has infinite range, but it might be far enough away that the strong force can't hold those two protons together. And so the bigger your nucleus becomes, the higher your chance for instability, for there to be too much electromagnetic force of repulsion and not enough strong force keeping everything together, and so that nucleus could decay.
Is that why uranium is the largest naturally occurring element?
No, yes, no. Okay. A lot more going on there. So, the largest stable natural element is lead. Anything heavier than lead, anything with an atomic number bigger than 82, is naturally unstable, naturally radioactive. And we'll get into radiation here in just a bit, okay? But anything above lead is too big for the strong force to keep it together and will eventually split and decay. The pattern of stability is not like linear, okay? But there are a couple of like rules of thumb that you can go by for determining stability. Basically, for anything with an atomic number less than 20, okay? I usually round this to argon because that's easier, right? I'm using one end of the periodic table, so I usually say 18, but 20 or less, right? So we're talking calcium or below, right? So all of those elements, okay, will be stable if they are at their most abundant isotope number. So for example, carbon 12, right? Carbon 12 is stable, but carbon 14 isn't, right? Carbon 12 is the most abundant or normal isotope. Any other isotope is going to be unstable. So for anything less than 20, if it's the isotope that's listed on the periodic table, you're stable. After that, you can kind of see the curve. The dots are the actual data for the isotopes. The dotted line would be the 1-to-1 ratio between, say, atomic number and number of neutrons. So basically what happens is you get higher and higher and higher. You need more neutrons in order to be stable. So the stable isotopes tend to run higher in their neutron count compared to their proton count. And those neutrons in those stable elements are basically keeping more glue in the nucleus, right? So that's one thing. So anything less than 20 stable as long as it's the chief isotope. Anything above 82 is going to be unstable naturally no matter what. And then for everything else in between, you just kind of look on a table to decide what isotope is radioactive and which one isn't. Again, we'll get into what all those things are. But one of the kind of key ideas here for when it comes to the tug of war that exists between the strong force and the electromagnetic force is this concept called binding energy. And binding energy is the question needs to be asked, where does the strong force get its energy to do its work? Right? It's a force that exists, but it's got to hold things together. So where does it get that energy to keep things in place? And the answer is it gets it from the mass of the nucleons themselves. As an example, the mass of a helium atom. So this is just naturally occurring helium. So the mass of the nucleus of a helium atom, okay, is 4.001506 atomic mass units. And again, using every sig fig that I can get. But if we wanted to build a helium atom, we're going to get out our Lego set and start building the universe, right? How would we build a helium nucleus? What goes into the helium nucleus? Helium is mass of 4, atomic number 2, so that means 2 protons and 2 neutrons. So we go grab 2 proton Legos and 2 neutron Legos, and 2 protons plus 2 neutrons, right? Now, the mass of a proton is 1.008665. And the mass of a neutron is 1.007276. So if we double this and then add it together, I get 4.031882 atomic mass units. The green box, almost a box, the green box is the result we get when you just take the mass of protons, mass of neutrons, double them, add them together. But the mass of helium as it occurs in nature is that. Bigger or smaller than what we get when we just add stuff together? It's smaller. Where did the mass go?
Energy.
It went into the energy that keeps that nucleus together. And the binding energy is the difference between these two masses. And I know that sounded weird. The binding energy is the difference in the masses. But when it comes to nuclear physics, energy and mass, same thing. E equals mc squared. Just arguing about speed of light squared, big deal. So, to find the binding energy, I take my 4.031882, I subtract off 4.001506, too many zeros, no, and I get a value of 0.030376 atomic mass units, which, when I use the conversion factor I showed you on the other screen, gets me 28.295 mega electron volts per c squared. And since E is equal to mc squared, I can just take my 28.295 mega electron volts per c squared, multiply by a c squared, and I get my binding energy of 28.295 mega electron volts. There's the energy that came from a mass, right? And that's the energy that is keeping the helium nucleus together. There's a different way to conceptualize this. When a proton or a neutron are in a nucleus, they weigh less than when they're free and on their own. You're used to thinking of protons and neutrons and electrons and all these things having the same mass or staying the same mass. That is not what happens. When a nucleon is in a nucleus, it has a smaller mass than if it was free and on its own. Why? Where did its mass go? It went into the binding energy. It went into keeping you stable. Because believe it or not, you are stable. You may not feel like you're stable right now. You are stable. I know because you are not decaying. And you might be saying, but Mr. Balogh, I am decaying. Please help me. No. Yes, but no. In some senses, you are very stable. This is a plot of mass number, total number of nucleons, versus binding energy per nucleon. So the binding energy per nucleon. So you take the total binding energy. How many nucleons are there in helium? 1, 4. 4 nuclei, right? 2 protons, 2 neutrons, total of 4, right? So you take the binding energy we found, divide by 4, and you basically get an idea for how much energy / mass is being taken per thing in that nucleus to keep it together. That's the binding energy per nucleon. Okay? As you can see, binding energy per nucleon, very low for hydrogen, and then very quickly as we go up the periodic table, okay, rises to a peak value around iron 56 and nickel 62. Iron 56 and nickel 62 are the isotopes that have the largest binding energy per nucleon of anything. That means the protons and neutrons in those isotopes are the least heavy things, right? When they're bound together. Which means there is a lot of binding energy per nucleon in those isotopes, which means those isotopes are very, very stable. So stable that you cannot produce any heavier elements without a supernova to get it to happen. We'll get there. Okay? So, keep all of that in mind, because what we have to talk about is the elephant in the room. Okay? The boogeyman, right, of radioactivity. And I hope by the time I'm done today, you will walk out of this room feeling a lot more confident about standing in the sun, and or more scared. I'm not sure which. But that also you have an understanding that you can't get away from it, and that's a good thing. We already talked about the discovery of radioactivity and Henri Becquerel, right? We left off the story, right, with Becquerel handing Marie her very first sample of radium. Marie and Pierre would work tirelessly at isolating and concentrating the radioactive element of radium that was in that sample of rock, and other samples that they gathered from the same mine. I think it was in Romania, and it would, over a period of a couple of years, right? They would work their chemistry and try to isolate this unknown element that gave off energy. They, in the process, would identify 3 different kinds of radiation: alpha, beta, and gamma. You should know that Marie would go on to not only win a Nobel Prize, but become the first person ever to win 2 Nobel Prizes, one for physics and one for chemistry. Pierre would tragically die in an accident. By all accounts, they were very smitten with each other. It was almost like kind of gaggy, right? How lovey-dovey they were. I mean, they worked together in the lab, and they loved each other. Right? Unfortunately, one day Pierre was walking home, he had a bunch of flowers from Marie, and he stepped in front of a carriage. Absorbed in his thoughts or whatever, we don't know. But he was run over by a carriage in the streets of Paris. Marie would go on, this happened after their discovery of radium, but Marie would go on to form a school for women to get them interested in the natural sciences. She would have a very public and sort of infamous affair with another scientist in Paris. She was quite the person, okay? But absolutely genius and absolutely dogged at science and methodology. To this day, her laboratory, her and Pierre's laboratory, is so radioactive that you are limited to the amount of time you can spend in the room. Her lab notebooks are kept in lead-sealed containers. The door handles, the keys, the cabinets, the metal fixtures are so bombarded with radioactive particles that to this day they remain radioactive. They would talk about how the samples would glow from the energy as they continued to concentrate, right? She would die of natural causes, but they would write in their lab books about how they would get these lesions on the backs of their hands, and they couldn't understand why their skin, right, was getting cut, right? They couldn't trace it back to any sort of chemical exposure. The alpha, beta, and gamma that they would discover, okay, turned out to have different charges. Alpha particles were positively charged. Beta particles were negatively charged, and gamma particles didn't have any charge whatsoever. And they knew this because charged particles get deflected by magnetic fields. And depending on which direction the charge would go, you could tell whether it was positive or negative. The beta particle would really turn really fast in a magnetic field, suggesting that it had very little mass. The alpha particle was a little bit harder to get it to turn, and so it had a larger mass. Fast forward, and we would understand that the alpha particle was actually a helium nucleus. So the radium was giving off, in its effort to become stable, the nucleus was kicking out 2 protons and 2 neutrons together, no electrons, okay? But it would kick out the helium nucleus, and that's what an alpha particle is. The beta particle would end up being an electron, a very energetic electron, coming from where?
Proton.
The nucleus. Electrons have no business being down inside nuclei, right? They're the fog around it, right? To be clear, this electron is coming out of the nucleus. Yes.
I'm trying to remember.
Mm-hmm.
It's not.
It's not the strong force. It's not the binding energy. What the hell? Where's an electron coming from?
Electromagnetic force.
Nope, more on that.
The neutron turns into a proton?
Yes, but that requires something else. The chargeless one, the neutral one, would also turn out to have no mass. So what does that mean it is? It's a photon. Okay? So I do want to answer some of the questions that I know are in your head. Okay? How much does it take to kill me, Mr. Baker? It's probably the first question. And you're too polite to ask it because it's too dark for, polite society. The answer is it totally depends. And we're gonna go there. We're gonna talk about the biological effects, right, of radiation on human tissue. Okay? Because we have ways to measure it and all that sort of stuff. We'll get there. But let's start off really simple because there's other things we need to talk about first. They are roughly labeled in terms of their ability to penetrate things. So an alpha particle really can't make it through a piece of paper. It really actually can't make it through more than 20, 30 centimeters of air before it will interact and become harmless stuff that you can put in party balloons. Okay? A beta particle, on the other hand, really can't, it can be stopped by a couple layers of clothing or a thin sheet of aluminum foil. A gamma ray go through just about anything, right? You need several inches of lead in order to stop a gamma particle. So there's a quiz I used to give, and I don't give it anymore because students will just get too angry. And the quiz goes something like this. I'm going to make you answer. I'll make you talk to each other, but you don't have to do it for points or on your quiz papers or anything like that. So let's pretend I baked you some cookies. Okay? And in the cookies, I give you 3 cookies. Everybody gets 3 cookies. And you get a cookie that has an alpha emitter in it, a cookie that has a beta emitter in it, and a cookie that has a gamma emitter in it, meaning there's a source in there that's giving off those radioactive particles, right? I give you the choice. You can hold one cookie in your hand. You can put one cookie in your pocket, and you can eat one of the cookies. What do you do? Where do you put the cookies to minimize your exposure to radiation? Turn to your neighbor and decide. One in your hand, one in your pocket, and one you eat. Go.
I feel like that's the more you want me and the alpha away from as it depends no matter what. I don't know if you're the words to reduce the amount of beta
All right. Which one do you hold in your hand? The alpha particle. Why? If an alpha particle can be stopped by a piece of paper, can it be stopped by your skin?
Yeah.
Easy, right? Okay. Alpha particles can't get in through your skin. Okay. Which one do you put in your pocket? Beta. Why? Couple layers of clothing, right? Can stop a beta particle. So the gamma one is left for you to eat. And why do you eat that one and not the others?
Because regardless of which one.
Inside or out, it's going to get you. Doesn't matter where it is. Okay? So, if you ate the alpha or beta, you would now be exposing your internal organs to radiation. So it's not to say that alpha and beta aren't dangerous. They are. And we've got to quantify that danger. We will do that. Not today. Probably next week. Radon is a noble gas. It is also what? Unstable. In other words, radioactive. Because it's bigger than lead, right? Isn't atomic number bigger than lead? Radon is a noble gas, doesn't react with anything, but is the byproduct of geological processes in the Earth's crust. It gathers in basements and any underground anything, okay? And gives off alpha particles. Normally, not a problem, right? You've got alpha particle shielding built into you. Until you go down into a basement and do what?
Breathe. Store food.
Breathe. Because what are your lungs doing? What is the purpose of your lungs? To pull a gas and put it in your bloodstream. Your lung doesn't sit there and go, oh, is that oxygen? I'll take that. It doesn't do that. It just takes whatever gas you give it and says, oh, bloodstream. So if you breathe in radon, that means radon gas is now in your bloodstream, and now you have an alpha emitter in your blood. And what is cancer of the blood called? Leukemia. And where are leukemia rates highest in our nation? In the Midwest. And why is that? We have more mountains and rock here in the West.
They have a lot more basements.
They have a lot more basements. And why do they have a lot more basements? Because they have tornadoes. Science. All right. Am I scaring you? Let's go through decay process really quick because I want to try to get to a simulation if I can. Okay. So kind of blitz this, and I might come back to this later to fill it out in more detail. But let's just talk about kind of what's going on here. In an alpha decay, Okay, in this case, radium-226. You're kicking out an alpha particle, and that's a helium nucleus. So notice how the mass number dropped by 4. Why did the mass number drop by 4?
Because it's kicking out the 4.
Kicking out a mass of 4, right? The helium nucleus has a mass number 4, and the atomic number dropped by 2 because there was 2 protons that left. So that means that the radium turns into what?
Radon.
Turns into radon. So radium, right here, okay, undergoing alpha decay, transmutes into radon. We know how to transmute the elements. In other words, turn one element into another. Under alpha decay, the atomic number will drop by 2. Mass number will drop by 4, but the atomic number will drop by 2. Change the atomic number, and you change the element. This exact decay process can be, not exact, it's a different isotope, is used in smoke detectors to keep you alive. What does a smoke detector do? Detects smoke. How does it do that? It knows when you're cooking, and it just goes off. No. It has a radioactive isotope in it. You pop open a smoke detector, you're going to see this label. I can never pronounce this word. Americium? Americium? Not good at that one. Okay. 241. Human-made isotope gives off an alpha particle. That alpha particle carries a charge, and that charge can be detected by a detector. And as long as those alpha particles are coming out of that isotope in a nice steady stream, the smoke detector knows that there's not a problem. But what happens if smoke starts to interrupt those alpha particles? What are those alpha particles going to do? They're going to get stopped. They're going to get deflected. They're going to get absorbed. And alpha particles really can't get through anything. And so the voltage drops from that steady positive rate of isotopes coming out, and the smoke detector knows that there's a problem, and it goes off. Radioactivity keeping you safe since the late 1950s. This is kind of a weird slide, but yes. Okay. Point is, the alpha particle drops and changes, right, the thing, and we can use that in very active ways. Here's a beta decay, and there's actually 2 different kinds of beta decay, and this is where things get really squirrely. Okay. So notice on the left-hand side over here, we go from carbon to nitrogen. An electron is kicked out. What? How does an electron come out of the nucleus? The answer is, we're not sure, but it might be this. A neutron can be thought of as a proton, but with neutral charge. You can't have 0 charge. So what does it mean to be neutrally charged? A balance, right, between positive and negative. And so if a neutron could get rid of its negative charge in the form of making it an electron, what would be left behind? Something with a mass of a neutron, but the positive charge, which in other words is more or less a proton. So what we think is happening is in the nucleus, in order to become stable, a neutron gives up a negative charge and becomes a proton. In so doing, it generates an antineutrino. What is that? Until the 1990s, we thought neutrinos were actually massless particles. We thought they were photons. Turns out they actually have masses, just very, very, really, really tiny. Matter of fact, neutrino, I think, is an Italian word for like little insignificant one or something like that. Okay? Nobody wanted it. Nobody was looking for it. They went and found it. Okay? Because in order for the energies and all that kind of stuff to balance, you had to have this other particle. Okay? So beta decay kicks out an antineutrino, an electron, which is the beta particle, and your atomic number goes up. You gain a proton. So in beta decay, in normal beta decay, you can actually increase the atomic number. Now there is a mirror to this, where instead of kicking out an electron, it kicks out a positron. A positron is a positively charged electron. Mass of the electron, but with positive charge. And then a neutrino comes out of that interaction, okay? And you can actually go the other way with it. Don't really worry about positron decay. I'm not going to ask you about it very much. I mentioned it here for completeness, okay? We'll focus on the beta decay that increases the atomic number. And then there's the gamma ray. The gamma ray is the one that is a photon comes out. This is closer to like Bohr's energy level transitions, where a neutron or a proton in the nucleus, how they're arranged, they could be in an excited state and they'll rearrange themselves and get into a lower energy configuration. And to do that, they have to give up energy in the form of a photon. So gamma radiation, gamma rays are photons that come out of the nucleus after the nucleus has sort of rearranged itself to be in a lower energy state. I know that was really quick. I'll go through and next time and we'll maybe do a little bit more detail. But the point is that we can now transmute the elements. The holy grail of alchemists everywhere was to do what? Turn lead into gold. How do you do it? Start with lead. Atomic number 82. What sort of radioactive decay do we need to trigger in order for lead to turn into gold number 79? Oh, okay, we do alpha. We get to mercury. Mercury's no good. So we do another alpha? No. Oh, platinum. Stop there. Right?
You do a beta decay.
So if we do an alpha and an alpha, and then a beta, we can turn lead into gold. Why are scientists not rich?
That sounds like it's just
That's really hard.
Because that's really hard. Like atomic bomb hard.
oh.
Okay? Lead is the last of the stable isotopes. Getting it to do an alpha decay, right? It's easier to put the sun in the bottle. And we haven't done that. So, while theoretically possible, impractical in the extreme. We measure radioactivity through something called half-life. Okay? And you need to, okay, so I'm going to pass out something right now. Okay? And let's see here. Okay, so I need everybody to take 3 of everything here, okay? There's going to be a container that contains dice. Don't sit there and pick the colors out that you want. Just take 3, okay? Try not to like roll them or lose them on the floor. I'm going to get you guys in the middle, right? Spread these out, right? Make sure everybody gets them. Okay? So you need 3 dice. And then take 3 pieces of paper. Paper. Make sure people on this side get it. Make sure people in the middle get it. Okay. Okay. You can pass those back up, and then we'll just leave them in the middle because you'll need a place to stick them. All right. So paper. All right. Half-life, okay, is a way that we measure the radioactivity of things. It is also the best video game franchise in all of history. I am not wrong, you are. Because in the Half-Life series, the hero, the protagonist, Gordon Freeman, PhD in physics, carries a crowbar. Yeah, doesn't talk. Actually, seriously, if you've never played the Half-Life series, you really do need to. It is gaming history. Okay, right up there with Zelda and Metroid and several others. Questions? No? About Half-Life? I can talk about this game all day long. Yes?
Then you go to MIT just to pull them.
Yeah, like, in particle physics. That's a little bit of a bad thing, right?
Opinion on the G.
What's that?
Opinion on the G, man.
Yeah, he shows up when he needs to. Okay, so what is Half-Life? Half-Life, what you need to understand is Half-Life is a statistical measure of an entirely random process that occurs when it comes to nuclear stability. Alpha, beta, and gamma will happen to a nucleus when it is unstable. Whether or not it's alpha, beta, or gamma depends on a lot of things, but the probability of decay is random. You can calculate it, but it's all based on a random event. But even though it's random, we can actually pull a useful measure out of all of that randomness, and that is called the half-life. So, what I've done, what I've given you are 3 die and 3 pieces of paper. I would like you to take your piece of paper, and I want you to crumple it up. Okay, make it into a tight little ball. All 3 of them. So you should have 3 balls. Okay?
Gotta give us paper cut.
Yeah, don't get paper cut. Okay? All right. You have 3 pieces of paper now, all tightly balled up, right? Okay.
What was the y-axis?
Number of nuclei. We'll do that in a second. Okay. You have 3 little tiny pieces of, right, and you have 3 die. Okay. By the power invested in me by the state of California, the fact that I control your future views of your grades, I now make you radioactive. You represent not 1, not 2, but 3 unstable nuclei that have a 1 in 6 chance of decaying. So each one of your die represents radioactive nuclei. There's roughly 33 people in this room, so that means that we have 99, close to 100, right, to begin with. 90, 80, 70, 60, 50, 40, 30, 20, 10. This is a little bit off, right? Okay. But 90, 80, 70, 60, 50, 40, 30, 20, 10, just to be nice and not clear. Okay. So what we're going to do is I'm going to have you, not yet, but I'm going to have you pick up all 3 of your dice. You're going to roll them on your desk. Not yet, not yet, not yet. Okay? If your die rolls a 1, you do 2 things. You're going to remove it from the pool and you're not going to re-roll it. Okay? You are going to take, for every die that shows a 1, you are going to take one of your pieces of paper and you are going to throw it towards the front of the room. The piece of paper is the radioactive alpha, beta, or gamma that you are emitting. Okay? The die represents the random chance that that nucleus is going to decay. What's the probability for our element here? 1 in 6, right? Every nuclei has a 1 in 6 chance of decaying. I will stand at the front of the room and I will count the number of radioactive decays that happen per time interval. And I will tell you when a time interval happens. So it's gonna go like this. I'm gonna say roll your die, you're gonna roll, you're gonna anything that's a 1, you're gonna push to the side, you're gonna take a piece of paper and throw it towards the front of the room, right? So if you roll 2 1s, what are you gonna do? Throw 2 pieces of paper. Okay. Here are the rules. Number 1, you will not hit me. Me, you get it out. Okay. Number 2, you're sitting in the first 3 rows. Duck. Number 3, you will not hit me. If you do have multiple ones to throw them one after the other, not 2 at the same time, or 3 at the same time. If you see somebody next to you throwing, just wait like half a second before you throw yours, right? I'm trying to count all the things that happen, right? So, only once. Now pick up your dice, roll them, for every one you get, throw it on the other end. Just once. Don't keep rolling. Don't keep rolling, just once. There's like 24 decays right there. Okay? 25. Cool. Let's happen. Okay? Alright. You rolled your die just once, right? I heard a lot of rolling. Okay. So, what's 100 minus 25? About 75, right? So if we put some marks on the time axis here. Now the time isn't really in seconds. The time's in Baloghs. Okay. We have, let's see, 75 remaining, right? Okay. All right. So how many of you, did anybody have all 3 of your die come up 1? You did? Yeah, it does happen. Okay. Right? How many of you still have all 3 of your die left? Okay. Right? How many of you only have 1 left? Interesting. Okay. So you can see it's kind of all over the place, right? Now, pick up your remaining die, roll them. Everyone. Okay, I counted 16 that time. Why was the number lower? What's 25? What's 75 minus 16? 59. There were fewer in the population, right? Okay, that sort of makes sense. All right, do it again. So there were 11 that time. What was that? 48? Like somewhere in there. Okay, do it again. Seven that time. That's 41, isn't it? Okay. Again. We done? So there was 6 that time. So is that 35? Somewhere in there. Okay. How many of you have all 3 left? How many of you have none left? Okay, and everybody else is somewhere in between. Do it again. Four. We're kind of slowing down here, aren't we? All right. Do you see a pattern emerging? We could keep doing this, okay? So for those of you that have, so how many of you have 3 left though? Okay, how many of you have 0? 1 left, 2 left. Okay, what I want you to do now, just to speed this up, you're going to pick up your die and you're just going to roll them repeatedly. You're going to count the number of times you have to roll. Remember the number you started with. Count the total number of times you have to roll for all of your dice to roll 1. When you're done with that, you can throw a piece of paper if you want. Go. All of them? You need to all go to 1. Count the total number of times it takes.
Yeah, roll on. Easy one.
Listen to how long it's taking some of these people.
14. One of them are 5 times.
All right, you can keep rolling if you want, but let's see. Luis Miguel, you started with 3, right?
Yeah.
How many rolls before they all went in 1?
6.
6. Deanna, you started with 3.
13.
12.
I went
Right?
really fast.
Yours went fast. How many of you had 1 and it took you like 20 times to get it to roll? Or some really high number? 10? Just with 1 die 10 times, right?
2 times.
How many people like rolled 20 or more times just to get their dice to go out? No? 15 or more? Yeah, okay, so like how many did you start with? 1 or 2?
Sorry, 2.
Okay, right? You can see here this is like totally random, isn't it? Okay? About when this is gonna happen. But we can fit a curve to this data. That curve right there, the number we have equals the number we started with, is an exponentially decaying curve that follows this equation right here, where lambda is not a wavelength. Lambda is called the decay constant, which is different for every nucleus. Okay? You guys are made of polonium, right? So let's measure the half-life of polonium. The half-life is defined as the amount of time it takes for half of your original sample to decay. We started with 100, 99. Okay? What's half of that? Roughly 50, right? So, we draw a line over till we hit our fit. We draw a line down, and it looks like polonium has a half-life of 2.8 Balogh. 2.8 time units. It would take another 2.8 time units to get down to 25 remaining nuclei. What just happened there? Half of a half. You don't like start with what you originally started with. Take half of the half, right? So after 3 half-lives, how much of the original amount remains? So 1 half-life wipes out a half. Then 1/4, right, for the second half-life. And then half of a fourth is an 8. Do you see what's going on there? Okay? It's not like 2 half-lives and you're done, right? 50 and then 0, right? You take half of the last thing you were at. Okay? All right. Come up to the front and get 3 pieces of paper and go back and sit down. Hurry. Need to have 3 pieces of paper again. So, if we've lost a piece of paper, I can give you another one. The janitors love me. Yeah, trade, do what you need to do to get 3 pieces of paper again. They tend to roll other places. So yeah, does anybody else need any paper? You got no paper? It's okay. All right. Now, we're going to alter the rules. This time, we're going to do exactly the same thing, only if your dice rolls a 1, 2, or 3, it's going to decay. So what are the chances of the probability of the decay now? It's half, isn't it? 50-50 chance? So, we've increased the probability of decay. What do you think is going to happen to the half-life? Is it going to get bigger or smaller? Okay, think about that for just a second. Also, take a look at the radioactivity of the sample. Radioactivity being the number of decays per time. Do you think the number of decays per time unit will go up or go down? So think about all those things. Pick up your dice. Roll once, and then throw.
Hey, you did better.
I didn't try to hit you.
Right, I counted 47. The first time I did this at Fresno City College, it was right after Gore lost to Bush in the 2000, and students demanded a recount. So we got roughly to like 50, right? Ish. It's kind of hard to. We'll put a dot right there. Okay, do it again. Just roll once and throw. So I'm making stuff up now, but it's going to be about right in there. Okay, do it again. How many of you are totally out? Yeah, right? Happened a lot faster, right? How many more decays are we having per time compared to the last one? A lot more, right? Okay. So which of these two were more radioactive? Polonium 1 or polonium 2? Polonium 2 is way more radioactive, right? There's more radioactive particles coming out of these decays in that time. If I come in here and I draw sort of the fit, it might be something like this, right? Okay. So is the half-life of Balogh 2 bigger or smaller than Balogh 1? It's definitely smaller. See, there's the 50, there's the half, and the half-life of Balogh 2 looks like it's 1 Balogh time unit. So what did we learn? We learned that radioactivity is all about the rate at which particles come out, right? We also learned that the more radioactive an element, the, fill in the blank, shorter the half-life. Uranium, 238. Uranium-238 has a half-life of 4.5 billion years. That's billion with a B. Like Bill Gates, Elon Musk billions. Right? Okay? 4.5 billion years. Our planet is 4.5 billion years old. So how much uranium is left in our planet? Half of what it started with. Uranium is often thought of as this really radioactive material, right? Okay. Iodine, I think, is it 127? I don't know. Don't quote me on the isotope. I'm not a doctor. Okay. But one of the isotopes of iodine, I think it's 127, 129, 127, has a half-life of like 12 minutes. Okay, they use it as a tracer in X-rays and other internal imaging. So they'll take this radioactive isotope, inject it into your bloodstream, and then take pictures. And that's considered safe under the doctor's orders and the necessity for doing it or whatever, right? The risk is not nearly large enough for the potential good things that could happen from detecting whatever it is they're trying to detect, right? And they don't have to cut you open to do it. Which of the two, iodine-127 or uranium-238, is more radioactive? Iodine by a long shot. Which one is safer? The iodine. By a long shot. They don't inject uranium into patients. Okay? Now, I worked with uranium in grad school. I told you this before. We used uranium as one of the layers in our thin film for our satellite layers. We had to learn all about uranium and its radioactive and chemical properties. And it was the chemical properties of uranium that were more dangerous than the radioactive properties. Radioactive properties of uranium, give up radiation. It can give you lead poisoning much faster than lead can. Like uranium can dissolve your kidneys like that, right? That's not radiation, that's chemistry, right? That isn't to say that you shouldn't be standing around the uranium sample for long periods of time, right? But radioactivity does not necessarily tell you how safe or dangerous a particular radioactive isotope may be.
What about cobalt-60?
Yeah, cobalt-60 is a big one. You don't want to stand near cobalt-60 either. Okay? So, in this form, calculating half-life is not very useful. There's another way to write this equation, and it involves us doing a little bit of a change of units, where we define the rate, the activity of a sample, as the number of events or number of decays per time. This has units, okay, of the Curie. A Curie, one Curie is 3.7 times 10 to the 10 decays per second. It's more or less the standard unit. You can see that one Curie is a lot of radioactive events per second. Most radioactive samples that are injected into patients are measured in like picocuries, okay, or nanocuries. A becquerel, 1 BQ, so this is 1 CI and this is 1 BQ, those are the symbols, is 1 decay per second. The becquerels aren't used very often. But this equation up here becomes your rate that you measure now is equal to the rate that the sample began with times this decaying exponential function. Half-life can be calculated if you take the natural log of 2 and divide it by the decay constant. I've now given you all the math that you need in order to do carbon dating, all that kind of stuff. I've run out of time to do an example of carbon dating. That's okay, I can do that next week. Okay? This homework isn't due until next Saturday or something, is it? We've got time, right? But very, very important thing for you to understand and know and do here at the end of class. Come up, put your dice in my buckets, pick up 3 pieces of paper, put it in the recycle bin. And I'll see you on Monday.
What is the half-life? What is that?
Natural log of 2 over lambda.